Cardiac muscles are branched. So with each branch point right here, so here's a branch point, here's a branch point, here's a branch point. The branch points are where one muscle cell makes contact with another and communicates with another muscle cell. And at the branch points, you're going to see openings called gap junctions, right? Again, when we communicate from cell to cell, they don't have eyes, they don't have ears, right? The communication is just moving of an ion from one cell to another. That's about it. Or you have some kind of protein that binds with another protein. That's the communication we're talking about between cell to cell. So as I stimulate one cell, right? If I stimulate this one cell over here, right? All the other cells it's connected to will also stimulate, because as this cell activates, right? The branch points allow sodium to go from one cell to the next, and it causes the next cell to hit threshold, which activates the next cell. Now you activate the next cell, that cell is also branched, and as it hits threshold, ions move to the next cell, causing that next cell to hit threshold. So as long as you activate one cell, all of the other cells it's connected to will activate in a very short time frame. So it's very important to understand that we need to activate the cells properly, because as soon as they activate, all the other cells it's connected to will also activate and depolarize. And keep in mind, just like skeletal muscles, these cells are slightly negative on the inside of the cell versus the outside. Remember, we call it the resting membrane potential, right? In a neuron, the resting membrane potential is about minus 70 millivolts. In a skeletal muscle, it's like minus 85 to 90. In a cardiac muscle, it's like minus 85 to 90. So when we stimulate it, we allow a little bit of sodium to enter, enough to hit threshold, where then voltage-gated sodium channels open. Hopefully that sounds like something you have kind of discussed before. I know in my class we have, and the reason why is because of this, right? Is because we're going to add on to it in just a few minutes. So you have the sodium channels open up, now sodium rushes in, and now you depolarize that cell. As you depolarize that cell, right, it goes, that depolarization, that wave, goes down the skeletal muscle, goes down the transverse tubule, allowing calcium to release. Again, the sole purpose of the action potential is to cause calcium release. As calcium is released, calcium binds to troponin, troponin moves tropomyosin out of the way, and then actin and myosin can pull and shorten. But in order for the actin and myosin to work, right, you need to move that gate, the tropomyosin. Tropomyosin prevents actin and myosin from making contact. So it prevents your heart from having a contraction when it shouldn't. Perfect, right? But in order to contract though, we need to move that gate out of the way. That's why calcium is so important. It allows for the release, right? It allows for the movement of tropomyosin. Now, if you remember that, perfect, right? Because it's identical to what we see in the skeletal muscle. If you didn't, just review it, right? I'm not going to ask questions directly on it, right? Because a lot of it is very so similar with the skeletal muscle. Just keep in mind that unlike skeletal muscles always require a motor neuron to activate, right? And if the motor neuron's damaged, the muscle can't contract. Cardiac muscles don't. They're autorhythmic. They will contract by itself. So if you don't give it the proper information, they will contract at different times. And we're going to see the atrial muscle, they want to contract at a much faster rate, 120 beats per minute, right? Where the ventricular muscles, they want to contract at a slower rate, 30 to 40 beats per minute. So there's kind of a mismatch, right? That's why the pacemaker is so important, right? The pacemaker kind of slows down the atrial contraction to 60, and it speeds up the ventricular muscles to 60. So then there's nice synchrony, nice uniformity. 60 beats per minute in the atria, 60 beats per minute in the ventricles. Perfect, that's exactly what we should see. Now, as we look at this, cardiac conduction system is the system that allows us to have this synchrony. So then 60 beats, right? Hopefully everybody's at 60, right? Keep in mind that if your heart rate at rest is 100, we say you're tachycardic. But that's true only at rest. Now obviously, if you're working out and your heart rate is 100 beats per minute, that's something, this is very minimal, right? If you're working out and your heart rate isn't 100 beats per minute, that means you're really not doing much, right? It should increase at least to about 100, right? So how do we increase or decrease it? How do we have this kind of communication? So then the atrius contract, then the ventricles. Atrius, then ventricles, with timing or synchrony. So we have this, the SA node. Now, when we look at the actual model, when we look at the real heart, you're gonna see there's nothing shiny like this, right? In reality, these are just modified cardiac muscles. So they don't look very different than the other cardiac muscles that are surrounding it. But I want you to think of them as almost pseudo type of neurons, right? The pacemaker is the one that kicks off the process of a heartbeat. In the heart, we call it the SA node, and it's found on the right atrial, on the sides of the right atrium. This SA node is called the sinoatrial node. Do you guys know if you guys ever watch races in like a track race in Europe, because we don't see a lot of it in America, right? So one of the things in track and field is you want to see world records, right? If you get a world record, you win more money. More people want to come watch you. So one of the ways for like a 600 or 6,000, right? Or some kind of long distance race, right? The 5K even, right? What they do then is if they want a nice steady pace, that's world record pace, they have a person that just kind of they call them the rabbit. And what they do is they know what the pace they should be running. They, instead of running all 6 miles or all 3 miles, they only run 1 mile, but they run it at a fast pace. So then everybody else that runs it will hopefully keep up with the pace, and then you will have a world record, right? That's a pacemaker. Same thing here. We have a pacemaker, and the pacemaker kickstarts everything. It's the one that activates first, right? This SA node fires first. As it fires, it sends that electrical discharge, the electrical signal, to the left and the right atrium, right? As it discharges, it causes the left and right atrium to depolarize. As it depolarizes, right, shortly after, remember, depolarization means that you have an action potential down that muscle, right? It takes a little bit of time for the action potential to go down the transverse tubules, so then you can release calcium, just like in the skeletal muscle. So as we depolarize the SA node, then the signal gets sent to all the atrial muscles. The atrial muscles also discharge and depolarizes almost immediately. As they depolarize, the atrial cardiac muscles will then allow calcium release. Then calcium binds to troponin, tropomyosin's moved out of the way, actin and myosin starts to contract, right? All because of this SA node discharging. So the first thing that happens is a discharge of the SA node. The SA node then causes the electrical stimulation of the atrius first. Shortly after the electrical stimulation, then the actual proteins interact, and now you'll actually have the contraction of the atrius. Now, because of the fibrous skeleton, right, the discharge of the SA node does not go into the ventricles, right? Remember, the fibrous skeleton insulates it. So then the discharge from the SA node stops, and you don't send it to the ventricles. That's important, right? So what happens? As the atrius contract, we're gonna bring blood into the ventricles here. And now we're gonna wait for the atrius to relax a little bit. As it relaxes, then we stimulate the second node, called the atrioventricular node. this is a node that will activate the ventricles, right? This node has fibers that goes into the septum called the atrioventricular bundle. Then in the septum, it splits into the right bundle branch and the left bundle branch. All right, these are just the pathways for those electrical signals. The left bundle branch goes to the left ventricle. The right bundle branch goes into the right ventricle. But keep in mind, as you're discharging right here, you're going to stimulate the apex first, and then you're going to stimulate each side at very similar times, right? So then we can contract at the apex, slowly squeeze, build pressure, and then squeeze up a little bit more, and then squeeze up a little bit more. So then you can do a lot more and more pressure, so then we can inject blood into the aorta, into the pulmonary trunk, right? Again, the synchrony is important. You need the left and the right sides to contract at very similar times, right? If they contract at very similar times, that means you'll eject blood at very similar times on each side. Perfect. Now, sometimes there's a delay on one side. If there's a delay on one side, then the left ventricle will eject blood first, and then the right ventricle ejects it a few milliseconds later, right? That can cause a problem if it occurs continuously, right? You'll have a mismatch of blood being ejected and then moving back in. Eventually, one side is going to fail, right? And now we have congestive heart failure. Now, we can measure these cardiac conduction system by measuring the output in EKG, right? And we'll talk about that probably on Monday. So in terms of cardiac conduction system, it all starts with the SA node discharging. Since it's the fastest one, as it discharges, it is the main driver. It's the one that causes all these atrial muscles to then depolarize and then contract. Remember, there's a difference, right? Again, you need to electrically turn on the cell first. As you electrically turn on the cell, depolarization, that causes calcium release, which then causes the muscles to contract, right? So you need to turn it on first. That's what the SA node does. It causes them to, the atrial cells, to electrically turn on. As it electrically turns on and depolarizes, then the calcium release occurs, and now the actin and myosin can contract, right? When the atria contract, you send the signal to the AV node, and the AV node just waits a little bit, right? Now it waits about a very short time, like 500 milliseconds. As it waits, it allows the atria to fully contract, ejecting blood to the ventricles, and it allows the atria to relax. Then you send the signal to the ventricles through the bundle branches, right? Now again, I'm saying it, it sounds kind of slow when I'm mentioning it. Keep in mind, this is happening instantaneously, all right? We, with our own eyes, all right, it's gonna seem like an instant, that there's no delay at all, right? But in reality, right, if we can measure it, we can see that there is a little delay. But if your heart rate is at 120, 150 beats per minute, that's pretty fast. That means you're like beating 2.5 times a second, right? That delay will be very minuscule, right? You're not gonna be able to see it, but we still can measure it. All right, so review this for the, the SA node, what makes it important, right? Specialized cardiac muscles, they generate spontaneous action potentials, triggering the atria to depolarize and then contract first. The AV node then receives a signal, slows it down, so it allows the atrial muscle to contract and then relax. Then it passes a signal to the bundle branches, which then contracts from the apex upwards, right? And that's very important to understand, that you contract from the apex up. Why? Because as you contract from the apex up, you're moving blood up into the great vessels. Right, the Purkinje fibers are the actual fibers that makes contact with the cardiac muscle. These are like the motor neurons, right? The motor neurons that releases acetylcholine that directly stimulates the muscle, while the Purkinje fibers are the motor neurons. SA node fires spontaneously at 90 to 100 times per minute. Again, if it is at 100 times per minute at rest, that's tachycardia. But what happens is this: the better in shape we are, the more parasympathetic activity there is, the lower the heart rate. Right? Again, the better in shape. So you hear and you will believe that, right, when Lance Armstrong, I know, right, Lance Armstrong, but you know Lance Armstrong was winning, like Ironman triathlons when he was a teenager, right? So he was a great athlete even before he started cheating, right? So he just, started cheating and became super famous and rich, right? It's hard to kind of blame him, right? He became super famous and rich, right? As a result of it. So what happens is, even when he was cheating, his heart rate was measured to be about 20 to 24 beats per minute at rest, which is crazy, right? So he had a lot of parasympathetic drive for that, right? Yeah, it's kind of crazy, right? If the heart rate is too slow, an artificial pacemaker is needed to kind of kickstart everything, right? And we'll talk about those, and we can actually see some. I'll show you some EKGs of people with artificial pacemaker. It's kind of weird that you can see, that this kind of mechanical thing is driving it. But, right, keep in mind, all it needs is some kind of discharge, right? All of these cells in the heart are autorhythmic. As long as you get a discharge, they will contract in response to it. Extra beats are formed at other sites are called ectopic pacemakers, right? So again, right, normally it's an SA node firing, but sometimes in some people, they'll have other areas that fire first. And then you'll have a beat that shouldn't be there. And if you guys ever had an ectopic beat, it's pretty common in females, right? When it happens, you know exactly when it happens. It takes your breath away, right? Because you're pumping the heart when there's no blood in there. And it can cause people to have panic attacks and things like that. Because if you are not expecting it, right? Obviously we don't expect our heart rate, all right, and the heartbeat, but when you are kind of having an ectopic one, you kind of, freak out in response. Caffeine, nicotine, anything that increases your heart rate can cause this. When we do have it, we can kind of cause an ablation, right? We'll kind of go in there, kind of kill those cells that are causing it, right? And again, that sounds really violent, right? But if you kill the atrial cells, it's not as important as killing the ventricular cells. We'll see why in a second. Right? Again, right, just review this, we kind of mentioned. I won't ask about the exact milliseconds on the test, right? Just understand that, right, the SA node fires, then we slow things down in the AV node, allowing the atrial muscles to contract and relax, allowing blood time to pool in the ventricles before we stimulate the AV node. And here it is, right here. All right, the last thing we'll talk about are these the electrical properties. I really want to get into this because then you'll have a weekend to kind of review this. They're like, yeah, like we're going to review it over the weekend. Right? And there's no more Super Bowl and football, so, right? And the Buck season, I mean, what game are they at right now, right? I think they're like 43-7, right? And the only reason I know that is because I just looked at it on ESPN, and they're great, but it's a long season, the NBA. It's way too long, right? Because, nobody cares unless you go far in the playoffs in the NBA. So let's talk about it. Hopefully you guys have time. If you didn't understand it, to go back a little bit. And if you didn't understand it, ask me questions on Monday, right? So to your left, this is a skeletal muscle. To the right, this is a ventricular cardiac muscle, right? Now, when we look at this, understand that for skeletal muscles right here, we start at a resting membrane potential of about minus 90 millivolts, right? Then we depolarize, right? In skeletal muscles, acetylcholine is released from the motor neuron, allowing acetylcholine receptors to open up. Sodium rushes in, you hit threshold, As you hit threshold, which they don't show here, then voltage-gated sodium channels open up at threshold, allowing lots of sodium to come in, allowing us to depolarize the skeletal muscle. Remember, depolarization is just turning the cell on electrically, right? That means you just have some kind of electrical charge moving down the cell. You haven't contracted yet. You start contracting halfway through, right? Right here. So now that we electrically turn on the cell, in the skeletal muscle, we turn it off right away. As we turn it off, we call it repolarization, and it's caused by voltage-gated calcium channels opening, voltage-gated potassium channels opening, and potassium leaving, right, the cell. Since potassium is positively charged, when potassium leaves the cell, it becomes negative again, all the way down to minus 90, right? Again, this is how we get a twitch contraction. If we want nice technique contraction, we have a lot of these occurring in a very short time frame. Now take a look, right? In a skeletal muscle, nice strong contraction, lots of these action potentials. As soon as you have one action potential and you recover, you have another one. As soon as the next one activates and recovers, you have another one. The faster the rate of the action potential, the stronger the contraction, the smoother the contraction strength. In cardiac muscle, if we did that, we will always have arrhythmias. That's not good. We don't want to keep stimulating it. So what we're going to see in cardiac muscle here is something slightly different. Look at the time here, right? For a skeletal muscle, it's only 1 millisecond between activation and recovery. In cardiac muscle, it's 500 milliseconds. So it's almost 500 times, not even, it's like 5,000 times as long, right? So here we have an activation that lasts almost 500 milliseconds. What's the difference? Well, when we activate the heart, we stimulate it once, right? And that stimulation lasts that whole distance, right? So in order to get contraction, all we have to do is stimulate it once. And then the contraction and the depolarization then lasts and lasts and lasts and lasts. 500 milliseconds instead of 2, right? It's a much, much longer span where we depolarize. That way we can have a much longer span where we can activate the cardiac muscle. So then the muscle can contract and build pressure from 0 millimeters of pressure till 130, right? So we stimulate it once, you have this prolonged depolarization phase, allowing us to contract for a prolonged period of time. Now, in cardiac muscle, the same voltage-gated sodium channels open up, allowing us to depolarize. See? Voltage-gated sodium channels, voltage-gated sodium channels. Same thing, right? So depolarization is the same, caused by sodium influx through voltage-gated sodium channels. The big difference is what we call the plateau phase, right? This plateau phase right here is what allows us to go to from 1 millisecond to 500 millisecond. It's only found in our cardiac muscles. And this plateau phase is due to this, voltage-gated calcium channels. So we didn't see that in the skeletal muscle because we didn't need it in the skeletal muscle. In heart though, cardiac muscle, right, in order to have a nice sustained long contraction, we stimulate it once and the depolarization lasts a long time. How come it lasts for a long time? Because as soon as we open up the voltage-gated sodium channels and we depolarize, a second group of channels open up. And these are voltage-gated calcium channels. And calcium entering allows us to have this really long plateau phase, which allows us to have a long sustained contraction. Right? So the next step right here kind of shows us how long it lasts. Right? This is our plateau phase right here. This plateau phase is caused by calcium going in. P is permeability. So this picture I like because it shows us, right, that when the permeability for something increases, usually is a sign that that substance is going into the cell. So right here, immediately, the permeability for sodium increases. Well, what does that mean? It follows our depolarization phase. So sodium coming in causes a depolarization. That's what it's saying. Right? Then you see the plateau phase right here. Right? Well, it can't be from sodium because look at how far sodium falls immediately. So it's not sodium causing that plateau phase then, because the permeability for sodium just drops off. So what's causing this plateau? Calcium. As calcium comes in, it allows us to extend our action potential from 1 millisecond to almost 500 milliseconds. Right? That's a huge increase in length. Then the same thing allows us to repolarize. Here, repolarization due to potassium. Skeletal muscles, repolarization due to potassium. Cardiac muscle, potassium. So here in brown is the potassium leaving the cell, and the permeability for potassium increases, meaning that it's exiting the cell. The exiting of potassium causes us to become negative again and repolarize. The big thing is this, right? The big take home is calcium is what allows us to have this huge length of time where we can build up contraction strength, build up pressure. So then that pressure can overcome, right, the blood sitting on top of your aortic valve and blood sitting on top of your pulmonic valve. There's heavy blood sitting on top of those valves, right? If you don't create pressure, those valves won't open. We have to create pressure so then we can pop open the top, right? And this allows us to, this long sustained contraction allows us to create pressure, which is perfect, right? Cardiac muscles, action potentials are conducted from cell to cell because of the branch nature of the cardiac muscle. In skeletal muscles, action potentials are only conducted along the length of the single muscle fibers. So some differences between the two, right? Again, the proteins are identical. Troponin, tropomyosin, actin, myosin, they're identical between the two. But there are some small differences. One of them is that cardiac muscles are branched. So if you stimulate one, the other ones it's connected to will also stimulate. Cardiac muscles, rate of action potential propagation is slow because of gap junctions and small diameter fibers. Meaning that, right, the action potential doesn't go as quickly down the length of the actual muscle cell. In skeletal muscle, it just goes super fast. But here in cardiac muscle, we're not talking about speed that's important, right? We're actually prolonging the contraction time. So speed isn't quite as important here. Synchrony is more important. Timing is more important. And then the last one's the part that I kind of highlighted more, calcium-induced calcium release. SICAR, we call it, right? So as we have calcium coming in from the extracellular space, calcium also triggers more calcium release from the sarcoplasmic reticulum. All right, now one of the differences that we see between cardiac and skeletal muscle is that cardiac muscle, right, allows calcium influx from the outside. We can't store enough calcium for that really long, plateau phase. So we have to let some of that calcium come in from the outside of the cell. So as that calcium comes in from the outside of the cell inwards, it causes more calcium release from the sarcoplasmic reticulum. And now you have a huge amount of calcium that's available to bind to troponin, to move tropomyosin out of the way. The more calcium, the more time you have to contract. The more time you have to create pressure. So then you can open the aortic and the pulmonic valves. Right? Now, I will stop right here, all right? Because I don't want to talk about the SA node quite yet, because I know it's going to get confusing. when we talk about it and compare these two. All right. Now, I have been known to have pictures like this on the written part of the test. Okay. All right. So you might see it, kind of understand these. This one and that one right there. Obviously, the other one is about skeletal muscle. And I'm not going to ask you questions about 201 in 202. Another hint, right? So, any questions so far? Who had no idea what we're talking about in terms of the action potential? Hopefully you have heard some of it, right? If you did, and you kind of understood it, go back and review it, right? Again, it's not as hard as you think. Basically, you stimulate it. How do you stimulate it? Voltage-gated sodium channels open. Sodium rushes in, right? Then the sodium rushes in. Sodium causes the next part to hit threshold. Now sodium rushes into the next segment, right? And now you have what looks like a, moving charge occurring, right? Each segment stimulates the next one, which stimulates the next one, which stimulates the next one, all right? Look, you have videotape, all right? All right, so that's how we kind of have to run it through, right? Again, review it if you need. I will have this online as well for you guys to look at. All right, let's take a little break. Actually, it's if you guys want to take a break, make sure you kind of have all your, like the models list printed. I'm gonna have you guys come back here and come back here